Hi everyone, I'm Chris Collison. We are deep into week 12 of the CHMP course on quantum mechanics at RIT for chemistry. And what we're going to think about today is the shapes of these particular orbitals that come about from the wave functions that were solutions to the Schrödinger equation for the hydrogen atom. And the thing that makes this particularly difficult is the fact that now we have three particular coordinates. We've got an r coordinate, we've got a phi coordinate, and we've got a theta coordinate. And so how do we start to visualize what the atomical orbitals are? Turns out we have to think about the radial case, and we also have to think about the angular description, perhaps separately. So let's go ahead and start digging into that. So let's start by recognizing that energy depends only on n for the hydrogen atom. The magnitude of the angular momentum is determined by L. And that's our quantum number L. And it's determined through this equation. So also the form of the radial wave functions depends on both of these quantum numbers n and L. And we've thought about that and looked at that in our Pogel review exercises. And so we've also recognized that when L is equal to 0, we call that an s orbital. When L is equal to 1, we call that a p orbital. When L is equal to 2, we call that a d orbital. And when L is equal to 3, we call that an f orbital. So these assignments are historical. And we've come across this before, of course, in general chemistry. And we also have a habit of describing wave functions, the radial wave functions, or actually the orbitals. We'll come to orbitals and a definition of orbitals shortly, but we have referred to a 1s orbital, for example, and that's the orbital where we have n is equal to 1. The energy is associated with the principal quantum number n, and we also have, this is L is equal to 0. And another example, 3D, for example, where n is equal to 3 and L is equal to 2. Okay, so that ties in with this D, where we have L is equal to 2. We also have m sub L, which is the magnetic quantum number, and it takes on 2L plus 1 values, right? It takes on, there are 2L plus 1 values for the magnetic quantum number. So that it comes down to the number of values it can take on comes down to the value of L. So these quantum numbers are linked together. We'll say it takes on, or there are 2L plus 1 values for m sub L. So another way of writing that is m sub L is equal to 0, comma, plus or minus 1, comma, plus or minus 2, all the way up to plus or minus L. And the z component of the angular momentum is determined completely by m sub L through the following expression. We have L sub z is equal to m sub L h bar. So the question now is, why is this called the magnetic quantum number? We know that it is associated with angular momentum in the z direction, but why the magnetic quantum number? Well, it turns out that the energy of the hydrogen atom changes depending on whether the atom is in a magnetic field or not. And that energy of the hydrogen atom depends on the magnetic quantum number. So let's take, for example, the 2p orbital. And we might imagine an energy level. So we're going to imagine energy on the y-axis here. And so when there is no magnetic field, we have a simple energy that is typical for a 2p orbital. However, when we apply a magnetic field, so here is in the case where there is a magnetic field, on the right hand side, what we say is that these 2p orbitals, they're actually split in energy, and the energies are shown, and this is known as the Zeeman effect. And we'll talk about this more in section 7.4 of the textbook. But it turns out that with this magnetic field, the energy E is determined by both N and M sub L. Well, as promised, we now get to talk about how we start to plot these wave functions. So let's have a look. So moving on, how do we plot the atomic wave functions? And the real difficulty here is that they depend on three variables. It's very typical to consider the radial and the angular parts separately. So, this should look familiar to you if you've done Chemical Activity 7, Chemical Activity 8, and also from Macquarie. Let's look at this radial wave function for the R1s orbital. So this is the radial wave function. And we also should think about the probability of finding that electron as we move away from the nucleus. And there's a kind of intuitive way of looking at this. So sometimes I think about the volume of a shell of thickness dr, and this helps me a little bit. So we can think of the volume of the shell of thickness dr, and it can be shown to be 4 pi r squared dr. Of course, the way that we've been thinking about this is to consider the volume element, actually. So if we go back to our spherical coordinates idea, so the volume element is simply d theta sine theta d phi dr r squared. So that's the whole sphere. Those are the coordinates that help us determine the whole sphere, d theta, d phi, and dr, but the volume element itself is given by this combination. Of course, if we separate out the angular component, so the integral d phi from 2 pi to 0, that's the angle around the equator, that's equal to 2 pi. And also, if we just consider the north to south angle, this ends up being equal to 2. Of course, the integral is minus cosine theta, so that provides us a 2 in there. So we multiply those two together, we end up getting this 4 pi part in there. Normalization will come into play, of course, later on, and that's why indeed we'll find that the y00 part for the 1s orbital, for example, is simply equal to 1 over the square root of 4 pi. So we'll come to that later, where indeed there is no angular dependence for the 1s orbital. But we're back to thinking about the probability of finding an electron at a certain distance away from the nucleus. So if we consider that when we're thinking about the distance from the nucleus, we're talking about this r squared term in here. So what we have to do for this 1s orbital in here, which is a function of r, so this is a real function, so therefore we don't have the complex conjugate. But when we're thinking about the probability, we have we're going to square this function. Okay, and now we've got the r squared dr term in here, so r squared dr, and that's the probability. If we consider the limits from infinity to 0, that's over all space. Of course, we know that must be equal to 1. So by the time we consider the substitution, we plug in our function for this 1s orbital. We can normalize this, of course, so we end up with the 1 term in here. But where are we going with this? What we really care about. So therefore, what we care about is perhaps the probability of finding that electron. And I'm going to draw your attention in particular to this radial function squared multiplied by r squared multiplied by dr. So this is, what does this really mean? This is the probability. This is a function that is the probability of finding the electron between r and r plus dr. So what we're now going to look at are some plots of this radial probability density function. So let's take a moment to have a look at some professionally drawn plots from the textbook that accompanies the class, but we'll do that in the next YouTube video. So click on and let's go take a look.